All right, hello everyone. I am Landon. And this is Smith's 181 math review. All right, so yeah, we have about an hour and a half. I'm not sure if we're going to be able to go through all the problems, but I think we'll be able to get through a good chunk of them. And yeah, I hope everyone was able to get through this beforehand. And also do want to mention that this is recorded. This will be uploaded to our the Math Center YouTube page within a few hours of now. And yeah, all right. So if you have any requests for problems, any questions or anything like that, feel free to just comment. You can just shout aloud, or you can comment in the chat. You can message me privately if you'd like. And yeah, is there any requests for problems before we start?
I was going to see if we could go over problem 2.
Problem 2. All right, let me take a look at that. Okay. All right. Anyone in particular you'd like to start with?
Well, a few of them I did get correct, but I was wrong on 2, the second one. So A2.
Okay.
Yep.
All right. Sounds good. All right. So let's take a look at this. So we have the limit as x is approaching 2, and then we have a minus right there. Okay. So we have 2 right here. I'm assuming this is associated with the first graph. And yeah. All right. So do you happen to recall what the minus means in the kind of exponent place?
Approaching from the left. I think I see what I did wrong, actually.
Oh, okay. Yeah, that's exactly right. So we're approaching from the left. We're looking at the lesser values of 2. So I like to think of it as like we're starting from 1, getting closer. And to me, I think it looks as if we're approaching this value right here, which I think is 1. Is
I think I
that?
got confused because it was an open circle, but
Hmm.
that doesn't matter, right? It's still considered the value of f of x.
Yeah, exactly. That's exactly right. If there's a hole right there, it actually doesn't matter to the limit. The limit will still be able to give us a value of what it's approximately.
Okay.
All right. Any other questions about that?
Nope, that one's good. And then number 4, though.
Number 4. All right, same part A.
Yeah.
Okay, sweet. All right, here, let me clear my whole mess I made. All right, so yeah, we're approaching x equals 3. Okay, so about right there.
Mhm.
Okay, so I don't see a plus or minus, so then that means both, right? So we're going to be approaching from this side and this side. All right, so let's see if there's any issues with that. I'm not thinking there is. There's no holes, there's no jumps, there's nothing weird like this, no asymptotes. I think, yeah, it's just from both sides, it's approaching, let's see, from the left, it approaches 3. And then also from the right, it approaches also 3. So
I believe
then,
the answer key says that that's wrong because I also put 3.
really, this is something else. Okay,
Yeah.
let me take a look at that real quick. Um, oh, I think there may be a typo.
Okay.
In part, so for problem 2, part A, part 4, it says as the limit is approaching 2 as opposed to 3 right here. So
Okay.
it says x going to 2 in the answer key.
Okay. So when x is approaching 3, it is 3.
Yeah, it appears to be 3.
Okay, cool.
And yeah, if it were to go to 2, so is it okay with everyone if I were to erase my work for a second? All right, if there's no objections, I'll get rid of that. If we were to approach 2, we're approaching from the left-hand side and the right-hand side, then we end up looking at the values of both of these. So then I'm pretty sure we found for this one, it's going to be 1. And then for the second one, coming from the right-hand side, it approaches 0. And these are not equal. Hence, the limit as x approaches 2 from both sides of f of x does not exist, since they're not equal. So I think that's what the answer key is coming from. But yeah, that's a good catch.
Okay.
All right. Would you guys like to keep going through these, or would you like to do a different problem?
I was going to see if we could go through B, 2B.
Sure. All right. Oh, specifically this one, or just 2B.
Yeah, 2B. Yeah.
Okay. Yeah. Sorry, I need to be consistent with how I'm wording this. Okay. All right. So yeah, let's start with the first one. So yeah, just as we said before, plus is, or maybe I'll start with minus, is coming from the left, and a plus is coming from the right. So we're coming from the right, and we're approaching 0. So then that means we are going this way, going towards 0. Okay, so if we look at that on our graph, I think it's approaching this value, right? Does that seem right?
Yeah.
Okay, yeah, so it seems like it's 3 there. And then now it says we're going and approaching 1. There is no plus, no minus, so then we are approaching from both sides. So let me erase this. And now we're going from this side and this side, going towards 1. So it looks like we have an issue. So this is, it's not continuous, right? Continuous means that we can draw it with one stroke of our pencil. It's just one long stroke, whereas this, we go, lift up our pencil, and then we start again going down. So then this is a jump discontinuity. So then we know if it's discontinuous, then that means there's no limit, right? It doesn't exist, because this one approaches, let's see, that one looks like it approaches 2, and this one approaches 1. So it's not continuous and there's not a limit there. Any questions on that?
Nope.
Okay, sweet. All right, so that one does not exist. Let me clean up this mess I made. All right, so now moving on to 3. So now it's having us look at each individual one. So yeah, we just ran through this. The left one approaches 2, and then the right one approaches 1. So in that order goes to 2, and from the right goes to 1. All right, and now they want us to go as x approaches 2 now, from left and right. Okay, so now we're going towards 2. All right. Any guesses to what this one would be?
0.
Yeah, exactly. It's going to be 0. Yeah, since both approach the same thing, this one goes to 0. We just look at the y value, and same with this one. It also approaches 0. Hence it exists, and it is that value 0. Okay, any questions before moving on?
Nope.
All right, sweet. And again, feel free to just comment in the chat if you have a question or anything like that, or just shout out loud. That's perfectly fine. Okay, should we just continue, or is there any other requests for problems?
Well, I do have a request for 4A and 4C.
Okay, sweet. All right. So 4A and 4C. Okay, algebra and limit laws to solve the limits. Okay, so yeah, let's start with A. Okay, so what do you guys think would be the first step when approaching a limit? What do you think we should do before trying anything else?
Factor the denominator.
Yeah, so we can factor. There's one trick I like to do even before that, is just to see if there is an issue. So let's just try to see if there is an issue with plugging in 3 everywhere in here. So let's see if that works out. I have a sneaky feeling it won't, but just to make sure, it's for our own sanity. Let's see if we plug in something. So if we plug like that, so this turns out to be 0 in the numerator, I think, if I can do math at least. And then we have, let's see, this ends up being 6, ends up being 3. This right here is 9, so that's also 0. So then we end up having, the way I like to bookkeep is I'll say form 0 over 0, which is an indeterminate form. So then there's an issue, right? But since there is, since it is an indeterminate form, we may be able to use a special trick to try to figure out what the limit is. Okay, so let me erase this work. All right, so yeah, let's try what you guys have said, factor. So does anyone happen to know what the numerator factors to be?
X plus 3, x minus 3.
Yeah, exactly. Here, let me clean this up a little bit, be a little more formal. Yeah, perfect. Okay, the denominator's a little tricky, but I have a feeling it factors. Does anyone happen to know?
X minus 3, x plus 1.
Minus 3, x plus 1. Let's double check that. So this multiplies to be minus 3, and then they sum to be minus 2, which is this number and this number respectively, and we're good. Sweet. All right, so we have what we want. Does anyone know what we do from here?
Cancel out the x minus 3.
Yeah, perfect. And notice that this is, if we were to plug in 3 for both of these, this is where our 0 over 0 comes from. So if we plug in 3 here, we'll get a 0, and we'll also get a 0 from this. And if we multiply 0 with anything else, of course, it's just going to turn to 0, and that's where, again, those zeros come from. So if we cancel them out, we have a potential to actually get somewhere. So yeah, let's cancel these out. And now we're left with the limit as x approaches 3 of x plus 3, x plus 1. All right, so what do you think we should do from here?
So I plugged in the 3 here, but I think maybe that's where I went wrong. I'm not sure.
Let's see. So generally, if you can plug in a 3, there's no weird indeterminate forms. Like you don't have the indeterminate forms that come to mind are like 0 over 0, 0 to the power of 0, and then maybe infinity minus infinity or infinity over infinity. These are all weird forms that we don't really necessarily know what the answer would be, just to kind of give an intuition. We know that any number over itself cancels to be 1, but we also know that anything where we divide by 0 is indeterminate. So the question is like, what is this? Is it 1 or is it does not exist or something like that? Similarly with this one, if we end up having 0 to the power of anything, it ends up being 0. But if we have anything to the power of 0, it gives us 1. So we have this conflict. So we don't necessarily know what this would be. So that's why these are, for the most part, bad. But let's see if that arises in any way. So we plug in 3 right here and right here. And then I think on the top we'll get, what, 6? On the bottom we'll get 4. And we get an actual number. We don't get anything weird like this. I think we can simplify that. Is that 3 over 2? Does that seem right?
Yeah, see, I think I simplified it wrong because I did 1 and 1/2. I don't know why.
Yeah, for sure. Yeah, sometimes that happens. I always get messed up on the arithmetic. But yeah, I think that seems to be a reasonable answer. Anyone have any questions on that?
Nope.
All right. So, here, let's just start with B. And then you had a request for C as well?
Yes, please.
Okay. All right. Yeah, actually, let's start with C first, and then we'll go back to B since you asked. Okay, so I'm going to clear all my work if that's okay. All right, so now we're working with C. Limit as x approaches -1 x plus 9 minus 3 over x. Okay, so yeah, first step, let's just see if we can plug it in, see if we get anywhere. So if we plug in, we end up getting something like, here, maybe we'll do this over on the left. So we get -1 plus 9. Can you guys see this color on this dark background, by the way?
Yes.
Okay, sweet. And then we have a -3 over -1. Okay, so this ends up being, I think that's the square root of 8, right? And then we have our -3 still, and then -1 at the bottom. And let's see, we can simplify the square root of 8 a little bit. Square root of 8 is 2 times 4. And then we can, the 4 is a square. It ends up being 2 squared. And then we break this up. This, the square root and the square cancel. So then we get a square root of 2 times 2, or written a bit more compactly, 2 root 2. And yeah, and I think this is all right. I don't think there's any issues with this. Ends up being, 2 root 2 minus 3 over -1. We can actually get rid of this minus if we want, just put it out here, turn that to a plus. And yeah, I think that's it's not an indeterminate form, it's just a number. And yeah, I think that's about it. This one's kind of tricky because I know a lot of times when you see a square root, you want to use that trick where you get a, you rationalize it, right? And you do that with the conjugate. I think it ends up being like x plus 9. You flip the minus to a plus, and then you don't want to change the expression, so you have to divide by the same thing, so that these cancel out just to be 1. And you know, you can multiply anything by 1 because nothing's going to happen. But yeah, we actually don't need to do that because we can just plug it right in, and we'll end up getting this, which is minus 2 root 2 minus 3, which is just 3 minus 2 root 2. So I just distributed the minus and I swapped the variables, or the values. And yeah, does that look accurate?
Yes.
Okay, sweet. Any questions on that?
Would it be correct if someone put -2 root 2 plus 3?
Negative, okay, sorry, would you mind repeating that?
-2 root 2 plus 3.
Plus 3. Yeah, of course. Yeah, that's fine. You're just swapping the two. We know that we can swap these two when we have addition or subtraction, just as long as we keep the sign up front.
Okay.
Let's see, I'm taking a look at the answer key, and it looks like it got a different answer. Did I write this down wrong?
Well, that's what I was concerned about, just because the answer key showed something else too.
Let's see. Okay, so if we plug in -1 everywhere, so that becomes a square root of 8, and then we have -3, -1 at the bottom. I don't really see an issue with that. Okay, let's try to see if we can figure out where that came from. So I know our immediate instinct is to want to rationalize. I just want to play around with that. Maybe if we rationalize something, maybe we'll get something a bit different. We should get the same answer hypothetically because we're not changing the expression, but I just want to see if maybe that's where some confusion came from on the answer key. Okay, so if it's okay with everyone, I'll just distribute this in. So of course we have to put parentheses around this since we're multiplying these two things. So we'll end up getting that, 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 and that. So I'm going to write on the bottom. So it becomes the limit as x approaches -1 of the square root of x plus 9 squared, since we're multiplying it by itself. And then we're going to have a plus 3 times x plus squared, or yeah, the square root of x plus 9, and then minus 3 x plus 9. That's quite nice. These two things will cancel. And then finally we have minus 3 squared. And then on the denominator we have x squared of x plus 9 plus 3. And we can actually distribute the x in. I'm not sure how much that will change. I think I'll just leave it as is if that's all right. And just clean it up a little bit. So then we end up getting, we can simplify the square root and the square. So we just get x plus 9 minus 9, since that's the 3 squared. These cancel, and we just get x over square root of x plus 9 plus 3. So there's just an x up top. Let me simplify that. So we can cancel this out with this, and there's just a 1 up top. And then, oh yeah, look at that. We get something slightly different. So then if we plug in limit as x approaches -1, actually, I'm not really sure why I'm rewriting that. I can just plug in -1 from here, right? So then this becomes 1 over -1 plus 9 plus 3. And this is square root of 8 plus 3 in the denominator. Let's see, 1 over square root of 8 plus 3, which we saw before. That's just 2 root 2 plus 3. I kind of have a sneaky suspicion that these two are more related than we think. Here, let me check something real quick, because I want to see if we can figure out why they put 1/6 there. Oh yeah. Okay, so it's actually, so our intuition was correct. This is actually the same thing as this, if you rationalize it. Yeah, you just multiply by the conjugate, kind of similar how we multiplied by the conjugate here. So yeah, these two are actually equal, despite them looking so bizarrely different. But yeah, so I'm not really sure where that 1/6 came from. Maybe it was a mistake. Maybe they plugged in like x plus, or rather x going to 1 rather than -1. I'm not really sure where that came from, but it appears to be this.
Yeah, because that's what I got as well.
Okay, sweet. Well, yeah, okay. Not really sure why that was. Is there any other questions regarding this? No? All right, so now let's move on to part B. Okay, I'm gonna clear all my work if that's all right. Okay, so now we have this guy. So this guy looks kind of intimidating. Let's see, how could we go about that? So this numerator is pretty gross. Let's try to see if we can clean that up a little bit before we start going into things. Well, I suppose, like always, it's always better to see if we can just plug it in directly. So yeah, before I clean it up, perhaps I'll do that. So let's see what happens if we plug in 4. And I can already see that the numerator is going to be 0. So that's not enough to determine the limit is something weird, because for instance, if the denominator was just like x, then we'll plug in 4, and then we'll have 1/4 minus 1/4, which is 0 over 4, but that's just 0. There's no issues with that. So you do have to check to see if the denominator is also 0, and that's not too hard to see. We'll end up getting, here, let me fix this. We'll end up getting 4 minus 4, which is also 0. So then we end up getting the form 0 over 0 again. And that's, of course, an indeterminate form. We have to do something. So let's try cleaning it up. Okay, so like I said, let's try to clean up this numerator. Let's do that by multiplying by some things. So I want to get rid of both the 4 and the x. I think that would make it look nice, right? So what do you think I should multiply on the numerator to try to get rid of both the 4 and the x? Any ideas? So what I would try is you can do them separately, but if you're in an exam, what I would recommend is actually trying to do both at once. So you can multiply by 4. So multiply both the numerator and the denominator by 4. And again, we have to divide by 4 as well because we don't want to change anything. We just want it to be 1. So we can do that, but we also want to get rid of this x. And we do that by doing the same thing. So let's just multiply by both. So we'll multiply by 4x on the numerator and the denominator. And if you do that all in one go, it's a bit faster in my opinion. So you'll be able to be a bit snappier on the exams. Okay, so now let's distribute to both of these. So in the numerator, we'll end up getting 4x over 4. And for the other term, we'll get 4x over x all over. And then I think this would be 4x squared minus 4 times 4, 16x, right? Actually, I think what I may do is sometimes it can be useful to keep the denominator exactly how it is. So actually, I'm going to just keep it like this for now and see if it helps us in any way. So now we can simplify. This cancels with this x cancels with this. So then we end up getting x minus 4 over 4x, x minus 4. And that's perfect because now we have an x minus 4 and x minus 4 here, right? So that's sometimes why it's useful to not distribute everything in, because you'll be able to get something to cancel. So now we just end up getting limit x approaches 4, 1 over 4x. So what would the answer be here, do you think?
1 over 16.
Yeah, exactly. So we just plug in 4 into here, and then 4 times 4 is 16. So then we just get an answer of 1 over 16 as our final answer. All right, any questions regarding that? No? All right, so that is 4. So now we finished 4. Is there any other requests for problems?
I was gonna see if we could go over 5.
Sure. All right, I'm gonna erase my work. And let me scroll down. Okay, all right, so we have squeeze theorem. So squeeze theorem is kind of a weird one, right? Squeeze theorem says that if you can jam your function between two functions as you're getting closer and closer to a limit, then if the limit of this and the limit of this are both equal, then the limit of that is going to be those two things, since they'll be the same. So let's see if I can kind of illustrate it well. So the way I like to imagine it is you have some form of plot, and you have a function, maybe I'm just making up random things, and maybe you have some other function. Oh, oops, that was bad. Something like that. So maybe if I call this G, and I'll call this H, the upper ones. That's the ones we're squeezing around. So maybe this is G, or rather, this is G and this is H. And if we look at this one point right here, maybe I'll just call this some random number, just call it A. They both approach the same limit point. And if we can show that our other function, maybe our function f, lies somewhere in here for all of time, then we know that it's forced to live in that limit point as well. It's kind of forced to pass through that little gap. And so we can say its limit point, this is f. Then we can say the limit point as x approaches a of f of x is equal to whatever the limit points of h and g are. Is that making sense? Am I illustrating that well? So that's
Yes.
kind of the intuition. Okay, sweet. All right, so now we just have to apply it, right? Okay, so we have to verify that we can use squeeze theorem, right? You may be able to just assume, since your professor maybe set it up just right. But how about we just first verify that the limit of this and the limit of this are both the same thing. So we have to figure out what is this value. Any ideas what this value would be, what we're approaching? So this would be like x is approaching what? What do you guys think that would be?
Maybe 1.
Let's see. So is it 1? So they give us the functions, and they say this is true for all x, and then they say find the limit as x is approaching -1. So I think it may be -1. But yeah, I think that may be what it is. Let's see if it works out at least. Okay, so now we're going to find out the limit as x approaches -1 for h, and we're going to do limit, sorry, my handwriting is horrible, as we're approaching for g as well, right? Okay, so limit as x is approaching -1 of g, which is -x² - 1. So let's verify this works, or rather, just plug in -1, right? So we plug in -1. The negative goes away because it's a square, but then there's a minus up front. So -1, -1, -2, right? Okay, so let's verify the other one does the same. All right, so we plug in -1. Okay, so you have to remember when you have a cube or an odd power, the negative remains, so it stays there. So it's going to be -1, -1, again -2. And there we have -2 and -2, and these are the same thing. So you can kind of imagine -2 less than or equal to f of x less than or equal to -2. You can kind of scratch this out with -1 roughly. And we see that it's trapped between -2 and -2. So then it must be, the only value in there is -2, right? So then the limit as x approaches -1 of f of x is equal to -2, this value here. All right, so I kind of over-explained kind of bit, but does that make sense to everyone?
So if you get the same answer for both of them, then that would mean that that is your final answer for the limit?
Exactly. Yeah.
So if it's conflicting, then what happens?
If it is conflicting, then we cannot use the squeeze theorem.
Okay.
So yeah, kind of an illustration of what that might be. So before we had our upper function, and then maybe I'll choose a different color. And then we had our lower function. So before we had it so that they had gotten really close at some point. So maybe like right there, where they had gotten really close, and maybe that's where our A is. And then that would mean f of x would have to squeeze its way in there. But now if they are different things, like for instance, maybe this ends up being -3 less than or equal to f of x less than or equal, maybe I'll just make it 2. So there's a drastic difference between this and this. Then that means f of x can be anything in here. So again, maybe I'll do a different color. So this is all f of x. So f of x, wherever you're approaching, so maybe x is approaching like 3, or maybe I'll do a different one. I'll do 1. So as you're going to 1, it can be any of the values in here. So any value between -3 and 2. And there's a lot of numbers between those two. So then we can't guarantee that is just one particular value. Is that making sense? Am I illustrating that well?
Yes.
Okay, sweet. All right. If you do have questions, feel free to interrupt me. But yeah, that was a great question. All right, so let's do part B. All right, so now I'm going to clear all this. Okay, so now this is our G, this is our H. So now we have to find the limit points of those. So if you're in a rush and you want to try to run through the exam as much as possible, we can kind of assume that the squeeze theorem does work. It's usually not good to assume, but usually your professor isn't going to set you up for failure, right? So you can just take the limit of one of them and just figure out one of them and then see if it works out. So this one seems like the easier limit to me. Let's see if we can figure that out. So it looks like A is going to be 2. A equals 2. So that's what we're approaching. So the limit as x approaches 2 of G, 2x plus 5. We can just plug it in, right? It becomes 4 plus 5. I think that's just 9, right? So yeah, if you wanted to be thorough, you'd also double check that this approaches 9 as well. If it does, then we know our answer is going to be 9. If your professor were to say verify or determine if we can use the squeeze theorem and solve the answer, then you would have to find the limit of this as well. And why not? We can just do that real quick. Limit as x approaches 2. X cubed plus 2x minus 3. So this isn't too bad of a function, just like the last one. We can just plug it in, and that's because it's a polynomial. Polynomials are really nice. That's because they're always continuous. They're always something like this, and you can guarantee that it will be, you can always draw it with one stroke of the pencil, right? So then we can just plug it in. So we get 2 cubed plus 2 times 2 minus 3. And let's verify that this is 9. This, I'm pretty sure, is 8. This is 4. And then we have a minus 3. So then this summed together just to be 1. And then we have 8 plus 1. And that is 9, just as we want. And there we are. Any questions about that? No? All right. So would you like to try would you like to move on to 6, or would you like to do a different type of problem?
Yeah, could we go over 6, please?
Sure. Okay, so problem 6, it says determine whether f of x is continuous at the following points. If it is discontinuous, name the type of discontinuity that occurs at the point. Okay, so part A says that x equals 3. So it looks like we're right here. And what do you guys think? Is this continuous or discontinuous?
Discontinuous?
Yeah, exactly. Yeah, so this is discontinuous. And that is because we can't draw it with one stroke of a pencil. We have to somehow draw it and then lift up, make a dot there, and then somehow come back over there. So this is discontinuous. Does anyone happen to know what type of discontinuity this is?
Jump?
Yeah, exactly. It's a jump because I have to jump my pencil over there to get to the next part of the function. So yeah, this is a jump discontinuity. Okay, all right, so now we're moving on to 6. So 6 appears to be this point here. Any issues with this one?
Doesn't look like it.
Yeah, that's what I'm thinking. It looks like it's fine. We can, all points around it, we can just draw a continuous line through it. But yeah, something you do want to keep in mind that, let's say, so this one's kind of a trick question I'll give you. So say you have some plot and then you have something maybe like this and then like that. So what if there was a point really close to it, like right here? Do you think at point A, would this be continuous or discontinuous?
Continuous.
Yeah, exactly. This is kind of a tricky one. We're really close to the discontinuity, but we're actually continuous because there is if we were to zoom in, there's a small neighborhood around the point A. So as long as you can draw a neighborhood around it, you're good. But when you have something like this right here, so maybe you're at that point, there is no small neighborhood where you can draw around it. You always have that jump you have to do whenever you go around this point A. So because of that, it is discontinuous. There's no small neighborhood. But yeah. Okay, so yeah, moving on to 9.
I did have a question.
Sure.
I think in the answer key, because for part B, I just put yes, it's continuous, but I think he put like something else, like explaining why it's continuous. So I didn't know if we had to do that or.
Oh yes, I see what you're saying. It says, yes, so it is using the formal definition of continuity. So here, let me clear my, actually no, I can keep that there. So the kind of the definitions I've been giving you are just intuitions, right? If you can draw it with a stroke of your pencil or if there is a small neighborhood around it, those are all kind of intuitions. There are formal definitions behind that, and that's precisely what he's doing. So the definition of continuity is that the point itself is defined. So you have, so let's say, yeah, let's single out 6 for a moment. So for f to be continuous at x equals 6, so you can just write at 6, but by this I'm trying to illustrate that the input x is equal to 6. So you can just replace that with 6. Yes, for this to be continuous at this point, we need a few conditions. We need f of 6 to be defined. So what that means is it's an actual number. So this equals some number, I'll just say like, I don't know, b or something. So there's an actual number. It's not infinity. It's not something weird. We can plug in 6 and get a number from it. So say this is a number. And do keep in mind that this is not infinity or a minus infinity. It's an actual number. And then the second condition is that the limit as x approaches 6 of f of x exists. So it has to exist. And do remember that means that for it to exist, the formal way you would say this is that the minus of it is equal to the plus. So that's what we were doing before. We're just checking if the limit on the left-hand side is the same as the one on the right-hand side. So this condition is very much associated with this. And then finally, the last condition is that f of 6, that value, is equal to the limit of x approaching 6. So these two things have to be real things. I like to imagine like it's something you can actually hold on to number, and they have to be the same. So those are the conditions that that they're checking. Yeah, it says f of 6 is defined, the limit exists and is finite. So by finite, they mean it doesn't go to infinity. And let's see, and it also says this last one saying that they're equal. Yeah, so those are the conditions required. Okay, does that make sense?
Yes, it does.
Okay, sweet. Yeah, the kind of, it's like why these properties, the intuition of why these are, this is kind of like mathematicians created these things so that you can have a real definition that you can work of drawing your function just with one stroke of a pencil. It's like, how do you actually put that down in concrete terms that you can draw your function with just one stroke? And that's precisely what these conditions mean. Yeah, it's kind of weird and unintuitive, but yeah, these just translate to drawing of one stroke of a pencil. So yeah, great question. Okay, so yeah, now we're at part C. So part C, what do you think this is? Continuous or discontinuous?
Continuous.
Let's see. So it's continuous.
Or
Okay.
no, open.
Yeah, that's what I'm thinking. I think it's discontinuous. Yeah, I see your, thank you for your chat, Anastasia. Yeah, I'm thinking discontinuous, and that's because of this condition. If we were to draw this with a pencil, we'd end up having to lift up our pencil and then begin again because we cannot fill in that hole. But yeah, these two both, or not this last one, but this one is true. But yeah, this one is not true. But yeah, sometimes it can be tricky. I always got messed up on these when I first started doing these. But yeah, so that's about it for that one. It's discontinuous. Oh yeah, that's right. We need to figure out what type of discontinuity you think this is. Yeah, exactly. It's removable. Yeah, if we were to removable, it's, I don't know, some of the names are kind of weird. I don't usually remember them, but removable just kind of means that you can pluck out the point, and that's kind of what the issue is. You plucked out the point. You can easily fill that in and then have it continuous at that area. Unlike this one where you cannot just put in a point and you'll be okay. This one is much stranger. Okay, and now finally the last one, part D. So what do you think about that one?
Discontinuous.
Yeah, exactly. It's discontinuous. What type do you think?
Infinite.
Yeah, exactly. It's an asymptote. There's no value defined here. So if you put in, if you wanted to try to find f of 12, your function is going to tell you, well, it's kind of like infinity. It's kind of going to infinity, but this isn't really this isn't a real number. So then this one again is not satisfied. The limit exists. That's kind of tricky on your definitions. As of right now, let's see. So there's a condition. If you look at the answer key for 6 part B, it says it exists and it is finite. I'm kind of being purposefully vague by that. It could be that your limit is infinite. In this case, it is. If you take the limit as you approach from the left or the right, you'll see that the limit ends up being, as x approaches 12, f of x ends up being positive infinity. And you can kind of argue, well, this is a thing. It is. They both from the left and the right, they approach the same thing. So why wouldn't the limit exist just like these ones do? That's a valid point. It actually does. You can say it does exist. So that's why your professor says and is finite, because it has to be an actual number you can hold. You can't really hold on to infinity, right? So yeah, that's kind of another thing you have to squeeze in here is finite. So yeah, this one is an infinite discontinuity. Okay, yeah, that's about it for 6. Any other questions about that? No? Yeah, so this one's a pretty important one for some of the further questions. I know that if you can get this down, then I think like problems like 7 will be a lot easier. But it kind of depends on how you go about it, though. Sometimes you can figure it out just by looking at it. But yeah, okay. So moving on to 7, or would you like to do a different type of problem? You want to move on to 7? All right, I'll take the silence as a yes. Okay, so start with part A. Okay, so it says determine whether f is continuous at the following points. Okay, so we have x equals 0 and x equals 1. So there's a couple different ways you can go about this. One thing I like to do is graph it. It is helpful because then you can translate your problem to this type of problem. And sometimes it's easier, but if you want, you can just try to look at it and see if it works out. So I can kind of briefly go through both ways if you wanted to see. I think if you're just to kind of eyeball it, you can kind of, it's a bit faster, but it's a bit more difficult, more likely to make mistakes. So here, let's give a go graphing it. So our first function is when you're less than 1. So let's label 1 right here. So if I call this like, maybe I'll call this like, actually I'll call this A and call this B. So this is like function A, function B. So function A is over here. Function B is over here. All right, and yeah, so let's start with the left. So it's the square function. The square function looks like something like that, right? So we're just going to draw that function just like we would normally, and then we stop as soon as we hit this line. So the question is, do we put a hole there or do we put a solid dot in? Does anyone know?
Solid dot.
Let's see. So solid dot represents it can be equal to. So I think we have strictly less than, so I think it'd be a hole there, unless I'm making a mistake. What do you think?
No, that makes sense.
Okay. All right, so I think there would be a hole there, and then we look at the other function, so function b now, it's 1 minus x. So 1 minus x, that's a linear function. Minus x looks something like this. And then we have a plus 1. So that means we're going to shift it up by 1. So then this point right here is 1. So wherever 1 is, maybe I'll call this 1. The function goes through here. And I think it would actually go through this point as well. But we're going to scratch everything on the left-hand side. So it just ends up being this. So now this is our function. So is it continuous at 0, you think? Any ideas?
I think yes.
Yeah, I think so. I think it is continuous there because we can just draw a little neighborhood around it. So yeah, I think that's good. So continuous there. What about x equals 1?
Discontinuous.
Yeah, exactly. It's discontinuous there. We got to jump discontinuity. So yeah, it's discontinuous there. And yeah. All right, so yeah, that's about it for that one. Let's take a look at the other way you can kind of go about this. Again, you have to be kind of careful with this, but it's a bit snappier, I think, in my opinion. So you don't actually have to graph it to figure out if it's continuous there or not. So what you can do is, let's start with the first point. So the first point, x equals 0. So the first step is to figure out where does this point lie. Does it lie in function A or function B? And I'm pretty sure it lies with function B because 0 is less than 1. So it would be in this domain. So then, now that we know it doesn't lie on the boundary, because that's really what you have to look for, is discontinuities can form at the boundary, the point 1, just as we have here when the points don't line up. If this function was shifted up like this, then you'd be good. That would actually be a continuous function because you can draw it. Let me do a different color. Because even though it looks weird, you can draw it with one stroke of your pencil. But since that is not the case, then it ends up being discontinuous. So anyway, so now that we found it lies in one region, all you have to do is check if this function is continuous. So x squared is a polynomial. All polynomials are continuous. So then you can just guarantee that this one immediately is continuous. And now we can do the next point. So x equals 1. So x equals 1 lies on the boundary. So then, since it lies on the boundary, we know that both these functions are continuous, but again, there could be the point of discontinuity where we have to do this jump. So you have to ensure that the limit as this function approaches 1 and the limit as the next function approaches 1, they both approach the same thing, just like how we use the ordinary definition of the limit. So we have to do the limit. So the limit as x approaches 1 from the left of x squared, we want, if these two things from the right of the other function. So the other function lives on the right of 1. So we put that there. If these two things are equal, if equal, then continuous. So I'm kind of borrowing some of those bulletin points we wrote down earlier using the definition of continuity. If they end up being the same, then we know it's continuous. And if it's not continuous, then we know it's discontinuous. Or, I mean, if they're not equal, then it's discontinuous. So you'll actually end up seeing that this is not true. This will result in 1, and this will result in, that'll be 0. And since they're not equal, then it means it's, so not equal, then it's discontinuous. And that's how we can get that immediately.
So I do have a question.
Sure.
So just to reiterate, you can just take the x and then plug it into the equation, and then if it's not true, then that is discontinuous.
Yeah, for the most part. Yeah, you just want to see which region does it fall in. If it falls in one entire region, like if it falls, if it falls over here or over here, just check if the function you're working with is continuous. If it is, you're good. But in the case that it lies in the other area, this in-between area, then you have to check that they both end up leading to the same thing.
Okay.
So I hope that answers your question.
Yes, thank you.
Okay, sweet. But yeah, that's kind of a quicker way where you don't have to spend all this time trying to figure out, oh, does this line, is it going to be moving up or is it going to be moving down? I know it sometimes can be time consuming. If you don't feel like graphing, this is another approach, but do be careful with it because there's a lot of room for error. But yeah. Okay, would you like to do one more? We could use the technique again, or we could just move on to a different problem.
Yeah, could we do 8 and 9 if possible?
Yeah, sure. All right, I'm gonna remove the work if that's all right. Okay. All right, so just part A?
Yes.
Okay. All right, so we're doing infinite limits now. So, yeah, okay. So I'm gonna write it right here just so it's a bit larger. Okay, so x is going to get really large when we want to figure out what happens. So essentially we're trying to figure out what happens to the asymptote as you keep going further and further to the right. So maybe it's something like this, where it approaches, it keeps getting closer and closer to this asymptote. Maybe it's something like that. And that, or then our value would be something like that. It could be that the case that it goes something like that though, or down. It can be doing various things, right? So what we can do is, there's a couple techniques actually. What technique comes to mind from lecture? Which way would you guys usually go about it?
I was having trouble starting it.
For sure. So there's a couple ways I think you can do it. I think the common way is by kind of do the trick where we did before, where you multiply by something and then divide by the same thing. You want to look for the highest power of x. So you can divide by 1 over that power. So if this was a 2, then we would multiply by 1 over x squared and then do that like that. But since it's only a 1, that's our highest power. Whoops. No, come on. There we go. Let's see if I can not erase the whole thing. There we go. Yeah, so since 1 is our highest power, we multiply by 1 over x and then another 1 over x. And then we just distribute that in. So then distribute, so 5 over x minus 3x over x, right? And denominator becomes 2 over x plus x over x. And we can just simplify, right? So this cancels with this. Perhaps I'll change colors to illustrate. This cancels that. That cancels with that. And then our new limit becomes 2 over x plus 1, just like that. Okay, any ideas what we would do from here?
I'm not sure.
So yeah, it's kind of a yeah, exactly. Thank you, Anastasia. So we can take the limit of each of these individually. So recall limit laws. We can turn this into the limit as x approaches infinity of 5 over x, and then minus 3. Kind of imagine this is just one thing. Minus 3 is outside of the limit. We can do that because there's no x's here. We don't have to worry about it. And then we do the same thing for down below. Plus 1. And now we just have to figure out these two limits. So x is going to get really large, right? If it's going to get really large, then that means we keep dividing by a larger thing. And if you keep dividing by a larger thing, it keeps getting smaller and smaller until it approaches 0, right? So if you want maybe a visualization, so you can bring this 5 out. Remember, there's a law of limits saying that you can bring this out and then just turn this into a 1. And similarly with the bottom one. So 2 here, put a 1 there. And look at the function 1 over x. So the mother graph of the function 1 over x looks like this. And it keeps getting closer and closer to 0. So it approaches 0. And that's precisely what this is. So yeah, we just keep getting closer and closer to 0, meaning this whole thing is 0. Just like that. And that's really nice. Now we just have 5 times 0 minus 3 over 2 times 0 plus 1. That's just minus 3 over 1. It's just minus 3. There. So then that means our entire function is going to approach something like that. So it's going to look, or oops, that's positive 3. It's going to look something maybe like that, where minus 3 is right there. So that's one way. This is a reliable way. Remember that you do just have to accommodate the highest power. The highest power here was 1. So then all we do is divide by the power of it's going to be 1 over x to the first power. There is a quicker way, though. I can give you a trick. It doesn't work all the time, but I can tell you when you can use it. So in the case where maybe you look at your function and you choose the highest power in the numerator and the highest power in the denominator. So notice how they're both to the power of 1. So we have minus 3x and then we have x. So I'm going to single these two out. And notice that if we cancel out this x and this x, we get minus 3 over 1, which is precisely what our limit is. And that's not really it's not just a coincidence, that's a general rule. You can just look at the coefficients of the highest powers. So when does this trick work? It works when they have the highest power term, when they're both the same, and you're approaching infinity. So remember, you have to be approaching infinity, and they have to be sharing the same power. If that happens, then you can just look at the coefficients of them and take the ratio of them. So minus 3 over 1, just minus 3. And that's the answer of your limit. So yeah, you do keep in mind for all these tricks I'm giving you, you may not want to do them on an exam unless if your professor wants you to show work, you may not want to just do this. You want to just do this as a general rule of thumb, or if you're really in a pinch, you can just write this down, right? But yeah, you generally want to show your work, right? So yeah, that's how that works. It does not work when they're different powers. So if you have minus 3x squared over x, it will not work there. But I can give you an intuition of how you kind of extend it for higher powers. So let's start with the next one. We can go about it this way as well, but I want to first show you how we can apply it to the next one. So we're going to infinity. It is negative infinity, but it still is a form of infinity. That's all that matters for this trick. We look at the highest powers. So again, if they were the same power, it'd be 3 over 2, but they're not. So think of this as 3 over x over 2x squared. You can kind of say it's roughly equal to it. Roughly, put that in like strong italics, bold, and quotes. But you what you can do is cancel out with this, and you end up getting 3 over 2x. And if you take the limit of this as it goes to negative infinity, then you'll end up getting, let's see, I think that would be, it'd be 3 over 2, or sorry, I'm not thinking correctly. This will keep getting larger and larger, and it'll blow up, and so you keep dividing by a smaller thing. So it'll end up turning into 0. In other words, this denominator dominates the whole function. It keeps getting much larger and larger in comparison to the entire function. And that is because of the power of 2. Kind of imagine taking the power, if this was like a million, if x was like a million, and x squared, you squared a million, it's going to be a million squares ridiculously more than x to the first. So that's kind of why this works, is as you keep going further and further to infinity, it's going to completely dominate the entire thing. So that's kind of the intuition. Anyway, yeah, it would appear as if this thing approaches 0. Well, let's double check that. So yeah, I kind of threw a lot at you guys. Does that make sense so far?
Yes.
Okay, sweet. Okay, so the limit as you approach this, so what we're going to do as we did before is divide by the highest power and the numerator and denominator. So we end up getting x approaches negative infinity, 3 over x squared plus 2 over x squared. Oops. 2 squared over x squared minus x over x squared plus 1. Okay, so just like before, this is going to become really, the denominator is going to become really large. So the whole thing is going to 0. Same with this thing. These are going to cancel out, and you're just going to get a 2. This is going to cancel out, and you're going to have 1 over x. And that's the denominator is going to get really large, at least in magnitude. I know there's a minus. We're going towards minus infinity. But if you divide by something like 1 over negative 10 to, I don't know, 100, this is still going to be really close to 0. So then this is going to go to 0, and then we have a plus 1 at the bottom. Oh, whoops, I forgot x squared then. And that's also going to go to 0. So then finally we have 0 over 2, which is just equal to 0, just as I said. So yeah, that's kind of how it works. Would you guys like to do the last one or move on?
Yeah, could we do C, please?
Sweet. All right, so yeah, so this one's a bit different than the other ones because of that square root. It makes it kind of weird. So we can actually apply that trick we used before, but again, we have to kind of fudge it as we did before. So this function is very similar to square root of x squared, just like that. the intuition of why we can just kind of roughly come to this is because x is going to get extremely large. It's going to be heading towards infinity. As it keeps getting closer to infinity, 5 is essentially nothing to it. If you took 10 to the power of 100, added 5 to it, that's virtually nothing. A computer wouldn't even store the plus 5 because this is so much more, uh, I don't know, magnitude. So we can kind of end up coming to this, simplifying it. X, we get rid of the square root, these cancel, and you get 6 over 1, which is just 6. And that's how you can immediately get the answer. If we want to do it a bit more, I don't know, a bit more rigorously, what we're going to do is look for the highest power. So the highest power of x appears to be x squared, but it actually isn't. It's because there's a square root on top. You can kind of imagine, again, these two things canceling, and you get roughly x. So then the highest power here is going to be 1. Okay, so let me scratch that out of the way so we have a bit more room. So we're going to multiply by 1 over x, 1 over x, just like that. Limit as x approaches infinity. So it's going to be 6x over x. And then we have, I'm going to write the 1 over x to the left. Okay, so we can clean up the numerator. So we just have 6 up top. Let's fix up the denominator. So the question is, how do we do that? Any ideas how we can get this somehow into the square root? No? Yeah, this one's kind of weird. So there is actually a trick you can do for this. So would you agree with me that 1 over x, the square root of x squared plus 5, that it is the same thing as the square root of 1 over x squared? Would you agree with me that these are the same thing?
Yes.
Yeah, so yeah, exactly. They are the same thing because if we were to simplify the square root, we just get that. So then we can just combine them into one square root. So don't forget the parentheses, x squared plus 5, just like that. And now we can simplify. So we get, or rather distribute, plus 5x squared. And now this is kind of what we want, right? We want to be able to cancel these things. And so we just end up getting the square root of 1 plus 5 over x squared. And that is more desirable because now our limit becomes 6 over 1 plus 5 over x squared. So this does actually just end up going to 0. But if you want to further justify why we can do that with it being in the square root, we can use limit laws. So the 6 stays up top, and we have the square root of the limit as x approaches infinity of 1 plus 5x squared, like that. We can bring the limit into the denominator and then bring it into the square root. And yeah, there's various functions we can bring it into, and that's because they're continuous functions. So then we can just make this go to 0, and then we end up getting exactly as we found before, 6 over 1, just 6. All right, I hope I didn't confuse more with the little tricks. I'm showing you guys those, I'm showing you guys that so that maybe you can run through an exam a bit quicker. But yeah, I hope they're a little helpful, kind of get an intuition of what's going on as well. But yeah, so any questions regarding that, how we got that? No? All right. Would you like to do sum of 9?
Yes, please.
Okay, sweet. All right, so I'm going to erase this. Is there any preference for A, B, or C?
Nope, no preference.
Okay. All right, so let's start with A. So it says find the equation of the tangent line to the graph at the given point. All right, so it's going to be something like we have some function and then we're given a point. Maybe that's the point. We want to find the line that just kisses the curve, right? So the way we can do that is by um, or actually, perhaps before going forward, I should ask where you guys are in the course so far. So have you guys been introduced to derivatives yet?
Yeah, we just did those yesterday.
Okay, so you are familiar with doing derivatives, right?
Yeah, a little bit.
Okay, is it, because there's a couple different ways of doing it. Are you doing it with the limit definition, or are you just doing derivatives, like kind of using all the rules of derivatives? I hope I'm illustrating that well.
Well, he was giving us like an equation kind of to use, like the slope, and then using the slope in the point slope form.
Okay, so here I'll write up two things. Just want to ensure um, ensure I'm going about it the right way. So there's this way, which is like ends up being f of, let's see, if I recall, it's f of something like that, and then we have x minus a. So this is one way to define the derivative, or you have something like this. Is it like, I think one particular rule I'm trying to get at is like this rule where you have maybe I'll just do x to the n is equal to n x to the n minus 1. Are you doing things like these or more like things like that?
Well, the equation was actually f of c plus h minus f of c over h.
Oh, yes, that's right. Use h. Yes. Yeah, so this is actually an alternate definition.
Oh, okay.
Or actually, if I'm remembering, I probably am remembering it wrong, but regardless. Okay, yeah, so x plus h minus,
I think it's c plus h.
oh, c plus h, okay.
And then minus
And
f
yeah,
of c.
c, okay.
Yeah.
C plus h, and then c, and then you just have h on the bottom, right?
Yes.
Okay, and that's as h is going to 0, is that correct?
Correct.
Sweet. Okay, so yeah, this is something you'll see very soon in the coming weeks if you haven't already. This is kind of this way is clunky. This way is a bit more, it's easier, but it's you need to develop more theory to get there.
Hmm.
Okay, so if we want to use the limit definition of the derivative, we need to use that to get the slope of this. So the equation of this line is going to be like y equals mx plus b, right? And we can figure out what b is by looking at the point, but what we really need is m. M is the slope of the line. And we do that by solving for this. When c is the point we're trying to, it's going to end up being that, right? So this is c, this is b. And yeah. Okay, so let's give it a go. We're a little short on time, so I'm going to try to get through this as much as I can. So limit as h is approaching 0 of f of, and f here, it's going to be x squared. So this is going to be minus 3 plus h minus f of minus 3 all over h. And then we plug these into our function, right? F of minus 3 plus h. We plug in everything for x. So it's going to be minus 3 plus h squared. So we just completely replace the entirety of that with this, and we end up getting that. And then we end up having the limit as h approaches 0 of minus 3 plus h squared minus, we're going to plug in minus 3 into that. So minus 3 squared over h. Okay, so what should we do from here? Do you guys happen to know? So we want to solve for this limit, right? So if we were to plug in 0 immediately, I think we'll end up getting something a little weird. We'll end up getting minus 3 squared minus minus 3 squared. And this is the same thing minus the same thing. That goes to 0. And then we also have 0 on the denominator. So we end up getting the indeterminate form 0 over 0, which is not what we want, right? So let's try simplifying this a bit before we do that.
I do have a question.
Sure.
I think he did with the point, like the 9 would be f of c. So you plug that in. I think that's what he did. I could be wrong though.
Yeah, that's exactly right. If you plug in f of minus 3, as I've defined f, this should be minus 3 squared, which is equal to 9. And that is what we have right here.
Oh, okay.
9. So yeah, it's kind of the same thing. I'm writing it a little differently than how your professor did, but yeah. Yeah, so now we want to simplify this a little bit. So factoring or distributing this out, I think we'll get 9 minus, I think 6h. I'm kind of skipping some steps if that's all right. Correct me if I'm wrong, but I think that's what we get. And then minus 9 all over h. These cancel. And then we end up getting, we can simplify this a little bit. So I'm going to swap them. So we have h minus 6h, oops, h squared. And then this turns out to be, if we factor, h minus 6. So then we have the limit as h approaches 0 of h minus 6 over h. These cancel, and then we get the limit as h approaches 0 of h minus 6, which is just equal to minus 6. And there we go. That is our derivative and also our slope. And yeah, so now we plug it back into the equation. We get y equals minus 6x plus b. B is going to be this coordinate right here. So it's going to be 9. It's the height of the function right there. Actually, wait, no, that's not necessarily correct. I apologize. I'm thinking of this in incorrect terms. I'm actually thinking of, I think this is slope, is this slope intercept? Is that the name? I forget the name of the equation lines, but regardless, this is the incorrect one. We actually want, if I believe it's y minus y1 equals mx minus x1, something like that. So this would be, yeah, I apologize, that's incorrect. This should be, this is still going to be c, but this is going to be x1 as well and y1, and we plug that in. So then we get y minus 9 equals m, which is still negative 6. And then we have x minus 3. And that becomes positive. And then we end up getting y equals minus 6. Distribute that. I think that's minus 18 plus 9. It got the 9 over to the other side. And then I think for our final answer, we get y equals minus 6 minus 9. Does that look right, everyone?
Yes.
Sweet. All right, and there's the answer. Any questions on that?
Nope.
Okay, sweet. Does the answer key say something different in the studio? Okay. Um, oh yeah, I see what you're saying. It's minus 6x plus 27. It seems as if they added these two numbers rather than subtracting them. Let's double check that. So this right here, I'm pretty sure in the formula is a minus. We definitely got the slope right, so we did our whole limit correctly. But the b component in our y equals mx plus b seems to be off.
That is the equation he has us use too.
He uses this equation?
Yes.
Okay. Yeah, okay, that's good. I think this is the point slope equation of a line. And yeah, I think we plugged in everything correctly. So this is minus 9 with the including this minus here. And then we end up adding it to the other side, so we get a plus 9. And then, yeah, I think maybe, unless I made a mistake, I think they may have accidentally kept that, they multiplied these two, but made this one positive or something when multiplying these two numbers to get negative, to get positive 18 rather than negative. But I think it's negative. But yeah. Okay. Yeah, I would double check with your professor because I'm pretty sure it's this. If you guys want a reference to double check some of your work, I recommend Desmos. Desmos is really nice. You can, here, let me get rid of all of this on the screen. So you can just graph a function x to the power of 2, and then find the point x equals, or actually, plug the point minus 3, 9. We can see that it's right there. And now let's try to graph our function. We had y equals negative 6x minus 9, if I'm not mistaken. And there we are. We can see that it just kisses the curve right there, and it goes through the point we desire. So I think this is the correct equation. But yeah, you can always use this to check your work when going about these. Okay, any questions on that?
Nope.
Okay, sweet. Yeah, that about does it for the review. I hope this was a little helpful, and yeah, I hope you guys do well in your exam and everything goes well.
Yeah, thank you so much for your help.
Yeah, no worries. And if you have any more questions, feel free to just come into the Math Center. We have tutors helping online and also in person.
Okay, thank you.
Have a good one, guys. Bye.